Hello everyone. So we have started a series in which we'll be covering each and every chapter of NCRT, and you can listen the NCRT from wherever you want. And as you know, your class 12 board exams are very near, and even your neet exams are near, and you need to be thorough with each and every line of NCRT. So in this series, we'll conclude with all the important chapters of NCRT, of chemistry, biology, and if possible even physics. So in the previous video, that is the first part of biomolecules, we have discussed carbohydrates, classification of carbohydrates and monosaccharides, and we have also discussed Fehling solution, Fehling's test and tolerance test, and we have seen that tolerance test and Fehling's test are given by monosaccharides, all monosaccharides, so they are called reducing sugars, and the sugars that give this test, they are called reducing sugars. Now let us talk about glucose, its preparation, and its structure and all other properties. Let's begin with the video. Glucose occurs freely in nature as well as combined form. Glucose occurs freely in nature as well as in combined form. It is present in sweet fruits and honey. So what is glucose? Glucose occurs freely in nature. Glucose occurs freely in nature. Glucose occurs freely in nature as well as in combined form. Glucose occurs freely in nature as well as in combined form. So glucose occurs freely in nature as well as in combined form. So this is important. Glucose occurs freely in nature. It occurs freely in nature as well as in combined form. It is obtained. So it is present in sweet fruits. Sweetness is due to glucose, and it is also present in honey. Glucose is present in honey. Ripe grapes, unripe grapes are sour to taste, but ripe grapes are sweet. Also contain glucose in large amounts. It is prepared as follows. Let's prepare glucose. So preparation of glucose from sucrose, cane sugar. So we have seen that glucose occurs in fruits, sweet fruits, honey, ripe grapes. Glucose occurs from sucrose. Sucrose is found in cane sugar, right?
No, it is.
Sucrose is found in cane sugar. Cane sugar is nothing but ganna, and also sucrose is found in our sugar. In sucrose, if sucrose is boiled with dilute HCl or H2SO4 in alcoholic solution, glucose and fructose are obtained in equal amounts. So what you have to do is, from sucrose you can prepare. If sucrose is boiled with dilute HCl, you have to take dilute HCl, or you can take any acid like dilute HCl, H2SO4, and that should be an alcoholic solution. You have to boil it with sucrose. Glucose and fructose are obtained in equal amounts. So this is nothing but hydrolysis of sucrose, that is acidic hydrolysis, because in presence of acid. So sucrose formula is C12H22O11 plus water. H plus glucose, fructose are formed. Now from starch, how can you prepare? Commercially, if you want to prepare glucose, glucose is prepared by hydrolysis of starch. By boiling it with dilute H2SO4 at 393 Kelvin under pressure. So hydrolysis of starch also gives glucose. So hydrolysis of starch by boiling it with dilute H2SO4 at 393 Kelvin under pressure. Pressure should be 2 to 3 Kelvin and temperature 393 Kelvin. So not much pressure, 2 to 3 atmosphere, just one more than normal 1 atm. Okay, so 2 to 3 atmosphere. C6H10O5 whole N, this is starch, or you can say cellulose. NH2O, that is N times water molecule, and H plus 393, 2 to 3 atmosphere, you get N molecules of N moles of glucose. N moles of glucose you will get. So you have to just do acidic hydrolysis of sucrose and or starch. If you do 1 mole of sucrose, you will get 1 mole of glucose, but if you take starch, you will get N moles of glucose. Let's talk about structure of glucose. Glucose is an aldohexose. It means it is having an aldehyde group, and is known as dextrose. It is a monomer of many of the larger carbohydrates Larger carbohydrates like starch, namely starch or cellulose. It is probably the most abundant organic compound on earth. Most abundant organic compound on earth is cellulose, right? Cellulose. Uh, Glucose is an aldohexose and is known as dextrose. It is monomer of many of the larger carbohydrates, namely starch, cellulose. It is probably the most abundant organic compound on earth. Most abundant organic compound on earth is glucose. It was organic compound on earth most abundant as glucose. It was assigned a structure given below on the basis of the following evidences. The first thing is its molecular formula was found to be C6H12O6. C6H12O6. On prolonged heating with HI is a reducing agent. It forms N-hexane. On prolonged heating with HI, it forms N-hexane, suggesting that all the 6 carbon atoms are linked in a straight chain. On prolonged heating with HI, it forms N-hexane. So HI is a very powerful reducing agent, and if you heat prolonged heating with HI, it will give N-hexane, means normal hexane, suggesting that all 6 carbon atoms are linked in a straight chain. That's why we got normal hexane, N-hexane, straight chain of hexane. So glucose, how can you represent it chemically? CHO, first carbon CHO, CHOH 4 times, then CH2OH, CH2OH, CHO, CHOH whole 4, CH2OH is glucose. On heating with prolonged heating with HI is a reducing agent. On prolonged heating you will get N-hexane. N-hexane is an alkane. Now talking about glucose, glucose reacts with hydroxylamine to form an oxime and adds a molecule of hydrogen cyanide to give cyanohydrin. Glucose reacts with hydroxylamine. What is hydroxylamine? NH2OH. NH2OH is nothing but hydroxylamine. It forms to form an oxime. Glucose reacts with hydroxylamine to form an oxime. So to form an oxime, glucose reacts with hydroxylamine to form an oxime and adds a molecule of hydrogen cyanide. Glucose reacts with hydroxylamine to form an oxime and adds a molecule of hydrogen cyanide to form cyanohydrin. So glucose reacts with hydroxylamine to form oxime. Okay, and glucose also reacts with a molecule of hydrogen cyanide to give cyanohydrin. These reactions confirm the presence of a carbonyl group, that is C double bond O, in glucose. So see, we have first taken glucose and we have prolonged heated with HI and then we got normal hexane. It indicates that all 6 carbon atoms are linked in a straight chain. Now to know the functional group, what we have done, we have reacted glucose with hydroxylamine and H2OH. Hydroxyl means OH, amine means NH3, so one hydrogen is replaced by OH, then H2OH. Glucose in the presence of NH2OH, it forms oxime. Oxime is nothing but CH double bond NOH group is attached. Remaining thing is same. CH double bond NOH is nothing but oxime. Then glucose also reacts with a molecule of hydrogen cyanide to form cyanohydrin, HCN. What happens is that CHO group is there, no? That is the bond between carbon and oxygen double bond is broken and CHCN and OH is formed. CHCN and OH is formed. Glucose gets oxidized to 6 carbon carboxylic acid gluconic acid. Glucose gets oxidized to 6 carbon carboxylic acid. Now glucose so now we have tested the presence of carbonyl group. Okay, in first reaction we have tested whether how many carbon chains are there, whether they are continuous, discontinuous, how they are. So we found that linked in a straight chain and hexane. Then carbonyl group is tested with hydroxylamine, that was giving oxine, and hydrogen cyanide was with cyanohydrin. Now let us talk about glucose. Glucose gets oxidized to 6 carbon carboxylic acid. So glucose, it gets oxidized to 6 carbon carboxylic acid, gluconic acid, on reaction with a mild oxidizing agent like bromine water. So glucose gets oxidized to 6 carbon carboxylic acid. So glucose gets oxidized to 6 carbon carboxylic acid. Glucose get oxidized to 6 carbon carboxylic acid, that is called gluconic acid. Gluconic acid on reaction with a mild oxidizing agent like bromine water. So bromine water is a mild oxidizing agent. So 6 carbon carboxylic acid, that is gluconic acid, is formed when glucose is oxidized with a mild reduced oxidizing agent like bromine water. Which water? Bromine water, Br2 water. That indicates that the carbonyl group is present as an aldehyde group. Carbonyl group is present as an aldehyde group. So first we have tested whether first we have got that yes, it is a carbonyl, but we don't know that whether it is aldehydic or ketonic. Then we have tested it with mild oxidizing agent. Then we got what? Gluconic acid. So we got that it is a aldehydic group. Bromine water is a mild oxidizing agent. So CHO group is converted to COOH group. That is then we got that this is a aldehydic group. Now acetylation of glucose, the fifth point, acetylation of glucose with acetic anhydride. So acetylation of glucose with acetic anhydride gives glucose pentaacetate, which confirms the presence of 5 OH groups. Since it exists as a stable compound, 5 OH groups should be attached to different carbon atoms. Now let's talk about acetylation of glucose. Acetylation of glucose with acetic anhydride. With acetic anhydride, glucose gives glucose pentaacetate. Glucose pentaacetate. Glucose pentaacetate, which confirms the presence of 5 OH groups. So acetylation of glucose with acetic anhydride gives glucose pentaacetate, which confirms the presence of 5 OH group. Since it exists as a stable compound, 5 OH groups should be attached to different carbon atoms. Okay. So then first we got 6 carbon straight chain. Second we got carbonyl group. Then third we confirmed that is an aldehyde but dealing with mild oxidizing agent like bromine water. Then fifth, acetylation of glucose with acetic anhydride, it gave glucose pentaacetate. This confirms that there are 5 OH groups. Since it exists as a stable compound, 5 OH group should be attached to different carbon atoms. Acetic anhydride. So it was giving pentaacetate. We confirm that it is having 5 OH group, that is on different carbon atoms, as it is a stable compound. Now let's talk about a very important thing, that is sixth one, on oxidation with nitric acid. Glucose as well as gluconic acid both yield a dicarboxylic acid on oxidation with nitric acid. So if you take nitric acid, glucose as well as gluconic acid both yield a dicarboxylic acid. Glucose as well as gluconic acid both yield a dicarboxylic acid, that is saccharic acid. This indicates the presence of a primary alcoholic OH group in glucose. So on oxidation with nitric acid, glucose as well as gluconic acid both yield a dicarboxylic acid. Glucose as well as gluconic acid both yield a dicarboxylic acid, saccharidic acid. This indicates the presence of a primary alcoholic OH group in glucose. See, if you do oxidation with nitric acid of glucose, you will get saccharic acid. And if you do oxidation of gluconic acid, you will get a dicarboxylic acid, that is saccharic acid. Saccharic acid. Saccharic acid. So glucose on oxidation with nitric acid, it gives saccharic acid, as well as what gluconic acid also gives saccharic acid. So glucose and gluconic acid both gives saccharic acid, and oxidation with nitric acid indicates that the presence of a primary alcoholic OH group in glucose. Primary alcoholic group. The exact spatial arrangement of different OH group was given by Fischer after studying many other properties. So now we confirm that there is a primary OH group, there is a carbonyl, that is aldehyde, there are 4 OH group. Now how is the spatial arrangement of different OH groups? This was given by Fischer after studying many other properties. Its configuration is quickly represented as 1. So gluconic acid is represented as 2, saccharic acid as 3. So its configuration is correctly represented. So the spatial arrangement of different OH group was given by Fischer after studying other properties. Glucose is correctly named as D plus glucose. D before the name of glucose represents the configuration, whereas plus represents dextro-rotatory nature of the molecule. D and plus is different. D and plus is glucose is correctly named as D plus glucose. D before the name of glucose represents the configuration. So capital D denotes the configuration, whereas plus represents dextro-rotatory nature. Both are not at all related. Capital D represents the configuration, plus represents dextro-rotatory nature of the molecule. It should be remembered that D and L have no relation with optical activity of the compound. It should be remembered that D and L have no relation with the optical activity. See, D and L, they do not have any relation with optical activity, capital D and capital L. They only represent configuration, whereas plus and minus, they represent the optical activity. It is rotating the light clockwise or anti-clockwise when we are testing with polarimeter. That is different. Capital D and capital L, it do not have any relationship with optical activity of the compound. Okay, they are also not related to letter D and L. The meaning of D and L notation is as follows. See, small d and small l represent the optical activity of the compound. Capital D and capital L, they represent the configuration. They do not have any relation with each other. No relation at all. So the letter D and L, they do not have any relation with small d and small l. See, small d is nothing but plus and small l is nothing but minus. Small d stands for dextrorotatory and small l stands for levorotatory. The glucose is small d, means dextrorotatory. The letters D, capital D or L before the name of any compound indicate the relative configuration of a particular stereoisomer of a compound with respect to the configuration of some other compounds. The letter D and L before the name of any compound indicate the relative configuration of a particular stereoisomer of a compound with respect to the configuration of some other compounds. So capital D and capital L before any compound, it indicate that relative configuration of a particular stereoisomer of a compound with respect to configuration of some other compound. It's just a relative configuration of a particular isomer of a compound with respect to configuration of some other compound. Configuration of which is known. Suppose one is known, then the other is automatically decided. So relative configuration of a particular stereoisomer of a compound. In the case of carbohydrates, this refers to the relation with a particular isomer of glyceraldehyde. See, in case of carbohydrate, this refers to their reaction with a particular isomer of glyceraldehyde. See, glyceraldehyde contains one asymmetric carbon atom and exists in two enantiomer forms as shown. See, if the OH group is at the right side, so it is capital D, glyceraldehyde. If OH group is at the left side, then it is capital L, glyceraldehyde. So OH right means capital D, OH left L, plus isomer of glyceraldehyde has plus D, capital D configuration. So plus isomer of glyceraldehyde as capital D configuration. It means that when its structural plus is in brackets, that is capital D and L. Capital D is plus in brackets. Isomer of glyceraldehyde has D configuration. It means that when its structural formula is written on paper following specific conventions, which you will study in higher classes, the OH group lies on right hand side of the structure. Right hand side of the structure. All those compounds which can be chemically converted to capital D, that is plus in brackets isomer of glyceraldehyde, are said to have capital D configuration. All those compounds which can be chemically correlated to capital D means capital D means plus in brackets isomer of glyceraldehyde are said to have capital D configuration, whereas those which can be correlated to capital L minus of isomer of glyceraldehyde are said to have plus L configuration. So whereas those which can be correlated to L minus isomer of glyceraldehyde are said to have L configuration. L configuration. So L configuration is L configuration minus in brackets isomer of glyceraldehyde is said to have L configuration. In L minus isomer, OH group is on left hand side. On left hand side OH group is there. On left hand side OH group is there in capital L or minus in brackets. Okay, OH group is on the left hand side. For right hand side OH group, if OH group is lies on the right hand side, then it is capital D. So with respect to glyceraldehyde, capital D and capital L, we can give configuration for assign configuration for glucose. For assigning the configuration of monosaccharide, it is the lowest asymmetric carbon atom. Lowest asymmetric carbon atom. See, from lowest from bottom, if you'll see, the bottommost carbon is not chiral, it is achiral. So if you see the carbon after bottommost carbon, that is from bottom second carbon, if you see, it is having lowest asymmetric carbon which is compared. Okay, so you have to take the lowest asymmetric carbon, which is second carbon from bottom, as capital D means plus in brackets glucose. OH on the lowest asymmetric carbon is on the right hand side, which is comparable to plus glyceride. So plus in bracket glucose is assigned capital D configuration. Other asymmetric carbon atom of glucose are not considered for this comparison. Also, the structure of glucose and glyceraldehyde is written in a way that most oxidized carbon in case of CHO is at the top. Most oxidized carbon is nothing but CHO, it is at the top. Also, the structure of glucose and glyceraldehyde is written in a way that most oxidized carbon is at the top. The structure of glyceraldehyde, glucose, that the most oxidized carbon is at the top. Now let's talk about cyclic structure of glucose. The structure 1 of glucose explained most of its properties, but the following reactions in fact could not be explained by this structure. So first point, despite having the aldehyde group, glucose does not give Skiff's test, and it does not form the hydrogen sulfide addition product with NaHSO3. Despite having the aldehyde group, Glucose does not give Skiff's test, and it does not form the hydrogen sulfide addition product with NaHSO3. With NaHSO3. With NaHSO3. So despite having the aldehydic group, so now the problem is it is having aldehydic group. We have tested with the oxime that it is having carbonyl. Then we have tested with bromine water. Then we found that it is having aldehyde group. Okay, no problem with that. But glucose does not give Skiff's test. Even though it is having aldehyde group, it is not giving Skiff's test, and it does not form the hydrogen sulfide addition product with NaHSO3. With NaHSO3, it should give hydrogen sulfide, but even though it is having CH group, it does not form the hydrogen sulfide addition product with NaHSO3. It's not forming. So what's the problem? The pentaacetate of glucose does not react with hydroxylamine, indicating the absence of free CHO. It means that free CHO is absent because the pentaacetate of glucose does not give the hydroxylamine, does not react with hydroxylamine. The pentaacetate of glucose does not react with hydroxylamine, indicating the absence of free CHO. The pentaacetate of glucose, it does not react with hydroxylamine. It indicates that the free CHO group is absent. That's why it might not be reducing Skiff's test. It might not be giving Skiff's test. Does not form hydrogen sulfide addition product with NaHSO3. The pentaacetate of glucose do not react with hydroxylamine. So this all indicates that free CHO group is absent. Something is there, that is cyclic CHO of glucose. So glucose is formed to exist in two different crystalline forms. Glucose is found to exist, okay, for which alpha and beta are there, which are named alpha and beta. These are the two different crystalline forms. The alpha form of glucose, this melting point is 419 Kelvin, is obtained by crystallization. The alpha form of glucose, that is melting point 419 Kelvin, is obtained by crystallization from concentrated solution of glucose at 303 Kelvin, while the beta form, melting point 423 Kelvin, is obtained by crystallization from hot saturated aqueous solution at 371 Kelvin. So glucose is found to exist in two different crystalline forms, which are named alpha and beta forms. The alpha form of glucose, it is having melting point 419 Kelvin. It's obtained by crystallization from concentrated solution of glucose at 303 Kelvin, while the beta form at 303 Kelvin by crystallization from concentrated solution of glucose. Its melting point is 419 Kelvin. Let's talk about beta form. Beta form melting point 423 Kelvin, slightly higher. 419 here, beta form 423. It's obtained by crystallization from hot and saturated aqueous solution at 371 Kelvin. So both are extracted from solution of glucose. Alpha form is obtained by crystallization from concentrated solution of glucose, while beta form is obtained by crystallization from hot and saturated aqueous solution. The behavior could not be explained by the open chain structure for glucose. The behavior could not be explained by open chain structure. This behavior could not be explained by the open chain structure for glucose. This behavior could not be explained by the open chain structure for glucose. This behavior cannot be explained. Why it is happening? Why it is not giving Skiff's test? Why it is not getting hydrogen sulfide addition product with NaHSO3? Why it does not react with pentaacetate of glucose, does not react with hydroxylamine, and why it is existing in two forms, alpha and beta? This cannot be explained from the open chain structure. So it was proposed that one of the OH group may add to this CHO group and form a cyclic hemiacetal structure. It might be forming. It was found that glucose forms a 6-membered ring. Glucose forms a 6-membered ring in which OH at C5 involved in ring formation. So it was found that glucose forms a 6-membered ring in which OH group at C5 is involved in the ring formation. This explains the absence of CHO group and also existence of glucose in two forms as shown. It was found that glucose forms a 6-membered ring in which OH at C5 is involved in the ring formation. It was found that the glucose forms a 6-membered ring in which OH group at C5 carbon is involved in ring formation. Glucose at C5 carbon is involved in ring formation. So fifth carbon from the bottom, like 1 2 3 4 5, fifth carbon, that is from bottom we can take second carbon. So fifth carbon from top is involved in ring formation. Fifth carbon from top is involved in ring formation. This explains that the absence of CHO group and also existence of glucose in two forms as shown below. So it was found that glucose forms a 6-membered ring in which OH at C5 is involved in ring formation. This explains the absence of CHO group and also existence of glucose in two forms as shown. That is, these two cyclic forms exist in equilibrium with open chain structure. So behavior could not be explained by the open chain structure for glucose. It was proposed that one of the OH group may add to the CHO group and form a cyclic hemiacetal structure. It was found that the glucose forms a 6-membered ring in which OH group at C5 is involved in ring formation. This explains the absence of CHO group and also existence of glucose in two forms. One is called alpha form and then is beta form. The two cyclic forms exist in equilibrium with open chain structure. So from fifth carbon, OH group is involved in ring formation. OH group may add to CHO group. So the lone pairs on the OH is donated to carbon. So carbon will form COHH and the oxygen is there in the ring. Okay. So this is beta and alpha forms. So they are existing in equilibrium with open chain structure. So look at the diagram. Fifth carbon OH, the lone pairs on the fifth carbon OH group will be donated to the carbon and the O single bond with carbon is formed. The two cyclic hemiacetal forms of glucose differs only in the configuration of the hydroxyl group at C1. The two cyclic hemiacetal forms of glucose differs only in the configuration of the hydroxyl group at C1 carbon, called anomeric carbon. If it is taking place at the first carbon, so it is called anomeric carbon. If it is taking from the first, if there is a difference in lowest symmetric carbon, lowest chiral carbon, then capital D, capital L configuration. But if you can see that if glucose hemiacetal, cyclic hemiacetal of glucose differ only in configuration of the hydroxyl group at C1, it is called anomeric carbon. Anomeric carbon, the aldehyde carbon before cyclization. So the two hemiacetal forms of glucose differ only in configuration of the hydroxyl at C1, called anomeric carbon, the aldehyde carbon before crystallization. Such isomers, that is alpha form and beta form, are called anomers. Anomers means if they differ in the only in the configuration of the hydroxyl group at first carbon 1, only in the configuration of hydroxyl group at the first carbon are called anomeric structures. Anomeric carbon. First carbon in which the configuration of OH group differs, hydroxyl group differs, they are called anomeric carbons. Means the aldehyde carbon before cyclization. Such isomers, that is alpha form and beta form, are called anomers. Alpha beta form are called anomers. The 6-member cyclic structure of glucose is called pyranose structure. See, alpha, beta, they are called anomers. 6-member cyclic structure of glucose, they are called pyranose structure. 6-member cyclic structure को pyranose structure. In analogy with pyran. Pyran means what? Pyran is a cyclic organic compound with 1 oxygen atom and 5 carbon atoms in the ring. 5 carbon atoms and 1 oxygen atom. The cyclic structure of glucose is more correctly represented by Haworth structure as given below. Cyclic structure is correctly represented by Haworth structure. Pyranose name is got because it is analogous with pyran. Pyran is a 5 carbon atom ring with 1 oxygen atom in the ring. A 6-membered ring, but 5 carbon atoms are there in the ring, 1 oxygen is there. The cyclic structure of glucose is more correctly represented by Haworth structure. It is given, you can see in the diagram. Fructose is an important ketohexose. Fructose is an important ketohexose. It is obtained along with glucose by the hydrolysis of disaccharide sucrose. It is a natural monosaccharide found in fruits, honey and vegetables. So the fructose part we'll discuss in the next video. So till then, subscribe to my channel and hit the like button. This gives me motivation and to improve my videos and make it more good. So thank you so much for your time. Thank you very much.